Hello, good evening, my dear students. Let me start the minimal polynomials today. Let me define the word minimal polynomial. A polynomial, the definition is very simple. As usual, a polynomial, I'll denote it by the notation p of x. A polynomial p of x in f of x. Here the notation is different. You know, this notation stands for what? Set of polynomial rings. Whenever we write x inside the square bracket, that indicates the set of polynomial rings. Okay, a polynomial p of x in f of x of lowest degree satisfying the condition, which one? P of t equal to 0 is called minimal polynomial of t. Okay, let me define the same statement in another way. A polynomial p of x in f of x is said to be with a minimal polynomial for t, where t stands for an element. Okay, if p of t equal to 0 and for all q of x belongs to f of x, that means q of x is also a polynomial, belongs to set of polynomial rings, and we denote it by f of x, such that degree of q of x is less than degree of p of x. What that p of x stands for? P of x is the first polynomial in f of x, whereas the q of x is the next polynomial in f of x. Here the degree of q of x is less than degree of p of x. That means if the degree of q of x is n minus 1, then the degree of x should be what? N. Then q of t, here q of t is not equal to 0. P of t equal to 0, but q of t is not equal to 0. Right. Let me define the another definition. An element t, what I said earlier, t is an element. Okay, an element t belongs to a of v is called right invertible if there exists an element s in a of v. Generally we denote the element by small letters, but in algebra of rings, I mean here in the computational linear algebra, we denote the elements by capital letters. S is also an element in a of v, such that the product of two elements ts is equal to st, and the product of these two is equal to I, the identity element, or we denote it by 1. Similarly, the left invertible. Right invertible means ts is equal to st is equal to I. The left invertible, to define a left invertible, there exists an element u in a of v, such that ut equal to I or 1. Remember, if it is right invertible, s appears on the right hand side. If it is left invertible, that element appears on the left hand side. Let me repeat. If it is right invertible, the element s, I mean the next element, not t, the element s appears on the right hand side. If it is left invertible, it appears on what? Left hand side. If t is both right as well as left invertible, that means ts is equal to ut is equal to 1. If it is so, then we write it as s equal to what? U. Let me define another definition. An element t belongs to f e is invertible. That means it is right invertible as well as left invertible. As we have seen in the ideals. Left ideal, if the left ideal is equal to right ideal, then we call it as an ideal. Similarly, an element t belongs to a of v is invertible. We call the invertible as regular if it is both right and left invertible. That is st is equal to ts equal to I or 1. Note an element an element an element a an element in A of V, that is algebra, which is not regular. If it is not regular, then we call it as what? Singular. Regular means what? Right invertible as well as left invertible or simply invertible. Invertible means regular. If it is not regular, then we call it as singular. Let me take one example. Let F be a field of real numbers. F is a field of real numbers. V be in f of x, that means set of polynomial rings. Then we have two mappings. S is a mapping from V into V. Similarly, T is also mapping from V into V, defined by two conditions. First one, Q of x of S is equal to d by dx of qx. The next one is Q of x of t, here we have S, here we have t, is equal to the integral Q of x dx over the integral limits 1 to x plus k, where k stands for integral constant. Then we have to show st is not equal to ts, that means right invertible is not equal to left invertible or left invertible is not equal to right invertible. Okay, let me consider the function, the polynomial over the product of two elements. Q of x is a polynomial that you know. Q of x of st can be rewritten as, using the composite function definition, Q of x of s of t, replacing Q of x of s by d by dx of Q of x, and this is replaced by integral. After integration, what we get? We get Q of x plus k. Since k is not equal to 0, that means st is not equal to 1. Similarly, Q of x of ts is equal to 1. St is not equal to 1 and ts equal to 1. That indicates st is not equal to ts. Now, a theorem related to the minimal polynomial. If V is a finite dimensional FDVS, that means finite dimensional vector space. Finite dimensional vector space over a field F, then an element T belongs to FV is invertible, that means regular, if and only if the constant term of the minimal polynomial for T is not 0. Okay, we have to prove this theorem. The proof is simple. Let me take a polynomial in x. P of x is a polynomial in x, and we denote the polynomial like this: alpha naught plus alpha 1x up to alpha k x to the power k be the minimal polynomial. By definition, P of t is not equal to 0, provided the constant term is not equal to 0. If the constant term is not equal to 0, P of t equal to 0. P of t equal to 0 means, since P of x is alpha naught plus alpha 1x and so on up to alpha k x to the power k, we have to replace that x by an element t. What we get? Alpha naught plus alpha 1 t plus alpha 2 t2 and so on alpha k t to the power k equal to 0, because P of t equal to 0. Since alpha naught is not equal to 0, keeping alpha naught separately, taking the remaining term to the right hand side, again simplifying. Okay, if you simplify this one, what we get? 1 is equal to minus of alpha 1 by alpha naught and so on up to what? Alpha k, alpha naught t to the power k minus 1, provided if we take t common from each term. I will replace that bracket by s. What you will get? If you replace that bracket by s, what you will get? St equal to 1, and we know that, what we know? St is equal to ts, therefore it is invertible. Conversely, if it is invertible, then we have to show that it is minimal polynomial. Minimal polynomial means p of t equal to 0, provided alpha naught, I mean the constant term, is not equal to 0. Okay. We have to show that the constant term is not equal to 0. That means alpha naught is not equal to 0. Where p of t, what p of t? P of t means we have to replace x by t in a polynomial. We get this. Suppose, let me prove this result by contradiction method. Contradiction method means treating a constant term, that is alpha naught, equal to 0. If alpha naught equal to 0, then polynomial can be written as what? P of x is equal to alpha 1x, alpha 2x squared up to what? Alpha k x to the power k. Since we want p of t, that means we have to replace x by t. And after replacing x by t and taking t common, we get this step. Okay. Now, what I do now, I multiply both sides by what? T inverse. If you multiply both sides by T inverse, we know that T inverse means 1, right hand side 0. Okay. That means what we get? We get alpha 1 plus alpha 2t and so on, alpha k t to the power k minus 1. Let me take another polynomial of degree less than what? P of x. Since the P of x is a polynomial of degree k, that means we have to take a polynomial of degree less than k. That means k minus 1. That is here. Be a non-trivial polynomial. Then the degree of q of x. Degree of q of x is less than degree of p of x. And q of t equal to 0. Actually, what we want? We want q of t not equal to 0. But here we have q of t equal to 0. That means it is contradiction. Contradiction means what? What the assumption is wrong. Therefore, p of x should be a minimal polynomial for t. Let me take one corollary. V is a finite dimensional vector space over a field F. If an element T belongs to F V is singular, singular means left invertible is not equal to right invertible, then there exists an element, remember, there exists a non-zero element in A of V such that St is equal to Ts equal to 0. Actually, what happens if it is regular? Remember, if it is regular, then St is equal to Ts is equal to what? 1 or I. Since it is singular, therefore St equal to Ts equal to 0. Okay, let me prove this corollary. Since A of V is singular, that means not regular. Not regular means not invertible. Not invertible means left invertible is not equal to right invertible. Okay, I'll take the help of the previous theorem, important theorem. That is a constant term of a minimal polynomial must be what? 0. Let me write the polynomial. Let p of x is a minimal polynomial. This is not ordinary polynomial. This is a minimal polynomial. That means it satisfies the given condition. What is the given condition? P of t equal to 0. There exists another polynomial q of x in f of x such that degree of q of x is less than degree of p of x. Then only we call it as a minimal polynomial. Since p of t equal to 0, therefore what we get? That polynomial equal to 0, taking t common and replacing that bracket by s. What we get? St equal to what? 0. This completes the proof of the corollary. Now, another theorem. If V is a finite dimensional vector space over a field F, then there is an element T in A of V which is singular. If and only if there exists an element V not equal to 0 in V such that Vt equal to, Vt means what? Image of V under T. We denoted by Vt equal to 0. Okay. Vt means image of an element under T equal to 0. Proof. Suppose there is an element T in E of V which is singular. There exists an element S not equal to 0 in E of V such that St is equal to Ts equal to 0. Since S equal to S, I mean the element S is not equal to 0, there is an element W in V such that Ws is not equal to 0. Okay. Now, what I'll do now, this is standard result. Keeping this standard result in mind, let me continue. I replace a vector or an element V by what? Ws, and since it is not equal to 0 in V, operating T both sides, Vt equal to Ws of T, again using the definition of vector space as well as rings, regrouping W of St, and we know that St equal to 0. Therefore, W dot 0 equal to 0. That means image of V under T equal to 0 for V not equal to 0 in V. Let me prove this, the converse part of this theorem. Suppose the image of V under T, that is Vt equal to 0 for V not equal to 0. What is our claim? We have to show that T is singular. Let me prove this result by contradiction method. That means assuming the T is regular. Regular means invertible. By standard result, there exists T inverse in A of V such that T dot T inverse equal to T inverse dot T equal to 1. Since Vt equal to 0, operating T inverse both sides, what we get? V equal to 0, which is contradiction. Which is contradiction means our assumption. What was our assumption? Regular. T is regular. T is regular is a wrong assumption. So the correct one is what? T should be what? Regular. So the all proofs are very simple. I hope you got it. So in the next hour, I'll take few more theorems related to the minimal polynomial. Thank you.